It is the year 1348. You are standing at the edge of the lifeline of your village. The air is cold, heavy with the scent of damp earth and wood smoke. You lean over the stone rim, your hands resting on granite that was placed here 3 generations before you were born. You have been taught that this era was a time of filth. You have been told that our ancestors were ignorant, drinking sludge from the gutter, helpless against the microscopic world they couldn't see. And looking down into this abyss, it is easy to believe that narrative. There is no stainless steel here. There is no digital display. There is no chemical smell of chlorine. But as you pull the water up from the deep earth, you're engaging in a system of survival that is far more sophisticated than we give it credit for. The water in this bucket is not sterile. It is alive. It contains minerals, trace elements, and a microbiome. Yet, for the people of this village, this well was not a gamble. It was a fortress. It smells faintly of stone, of iron, of the earth that protected it for decades. It is cold enough to numb your fingers, heavy in a way bottled water never is. We often confuse technology with machines, but a machine is just one type of technology. A system is another. The medieval approach to water was not about sterilizing a liquid to perfection. It was about engineering a relationship with the geology beneath their feet. Today, we have achieved what kings and emperors could only dream of: instant, flowing water in every room. But to achieve this, we had to make a trade. We traded the stability of the earth for the fragility of the grid. We traded the slow filtration of stone for the fast chemistry of the plant. So, we must ask the difficult question. Not which water is cleaner, because the laboratory answer is obvious. We must ask something else. Which system is safer? If the pump stopped tonight, if the pressure dropped, how long before your tap becomes a liability instead of a luxury? And what if safety was never about sterility, but about structure? Because if this system fails, you don't lose comfort. You lose water, and you lose it immediately. That is the difference. To understand why, we have to go back. To understand the medieval water system, you must first understand the concept of the biological desert. We know from the study of historical food preservation that our ancestors were masters of creating environments hostile to bacterial life. A rural medieval well was not simply a hole in the ground. It was an inverted tower. The deeper they dug, the further they moved away from the biological chaos of the surface. Surface water, rivers, streams, ponds is warm and exposed. It is, in scientific terms, a high-risk zone with a water activity level perfect for pathogen growth. Surface water is warm and exposed. Deep underground, cold stone filters and slows everything down. The earth itself became the first treatment plant. But the most critical factor was temperature. We know from the preservation of ham and bacon that temperature control is the first line of defense against decay. A smokehouse had to be kept below 30 degrees Celsius to work effectively. Above that, bacteria multiply. Below that, they slow down. Deep groundwater sits at a constant, chilly temperature year-round. This is the cold chain of the natural world. In this dark, cold environment, the rapid bacterial blooms that plague surface water are suppressed. The water wasn't treated. It was harvested from a zone of safety. However, the medieval mind understood redundancy. They knew that water could sometimes betray them. When the source was questionable, they applied what food scientists today call the hurdle effect. Just as a cured ham is protected by the combined hurdles of salt, smoke, and drying, medieval beverages were protected by processing. Small ale, the daily drink of the era, was not consumed primarily for intoxication. It was consumed for safety. The brewing process involved the boiling the water, which thermally destroyed pathogens. But the second step was chemical. Fermentation drops the pH of the liquid. We see this same principle in smoked meat, where organic acids lower the surface pH to around 5.0. Most pathogenic bacteria, including E. coli and Salmonella, crave a neutral environment, a pH between 6.5 and 7.5. When you drop the pH, you create a chemical environment that attacks the cell walls of the bacteria. When water turns sour, bacteria struggle to survive. The environment itself becomes hostile to them. This is sophisticated chemical warfare. The medieval peasant didn't know what a hydrogen ion was, but he knew that sour water ale, cider, wine didn't make him sick. This system was defined by decentralization. Every village, often every cluster of homes, had its own source. If a cesspit leaked into a well in the next valley, your water remained safe. The failure was contained. It was a modular system. High effort, yes, but high resilience. Imagine being the one responsible for this well. If it fails, children drink first. If it fails, the elderly feel it before anyone else. There is no customer service, no emergency hotline. Water was not background noise. It was a daily responsibility. We must not romanticize this. This system worked beautifully in rural low-density areas. But in the growing cities, London, Paris, Florence, the system collapsed. When density increased, the distance between the latrine and the well decreased. The natural filtration of the soil was overwhelmed by the volume of human waste. In the cities, the fortress was breached, leading to the horrific outbreaks of cholera and typhoid that would eventually force the modern era to begin. The medieval system was not perfect, but it was independent. It required no electricity, no chemical imports, and no central authority. It was built on the laws of physics and geology. But independence has limits, and scale changes everything. What works for a village does not work for 1 million people. Now the story becomes more complicated. If the medieval system was a fortress, the modern system is a factory. We process water the same way we process industrial food, broadly, chemically, and at massive scale. The heart of modern water is chlorination. Chlorine is the curing salt of the water supply. Just as salt binds to water molecules to deny them to bacteria and meat, chlorine acts as a residual disinfectant. It travels with the water, a chemical bodyguard, killing pathogens that might enter the system. It is a miracle of public health that has saved more lives than perhaps any other invention. But once the water leaves the plant, it enters the distribution network. And this is where the factory model reveals its vulnerability. We pump this sterile water through millions of miles of pipe. Much of this infrastructure is aging, cracked, or reacting with the chemistry of the water itself. Inside these pipes, we fight a constant battle against biofilms. Even in chlorinated water, bacteria can form a slime layer on the pipe walls. Inside aging pipes, bacteria can hide in protective layers. If pressure drops, they enter the water unnoticed. We do not rely on the water being naturally safe. We rely on keeping it safe through constant intervention. And then, there are the additives we accept. In the meat industry, producers use loopholes like celery powder to add nitrates while claiming the product is natural. In the water industry, we manage contaminants like PFAS and microplastics by setting acceptable thresholds. Because our water comes from surface sources, rivers and reservoirs that collect runoff from roads, farms and factories, it contains the chemical footprint of our civilization. The medieval aquifer might have contained bacteria, but it did not contain pharmaceuticals or industrial Teflon. We have traded biological risk for chemical load. Ask yourself something simple. When was the last time you wondered where your water actually began? Not the tap, not the pipe, the source. But the greatest vulnerability is not chemical. It is physical. Modern water systems rely on pressure. Massive pumps powered by the electrical grid keep the water moving. This positive pressure is what keeps contaminants out of the pipes. If a pipe cracks, the water pushes out, preventing dirt from getting in. But if the power fails, the pumps stop. The pressure drops. And when the pressure drops, the system experiences backflow. Groundwater, soil, sewage, everything outside the pipe can be pulled inside through the smallest crack. And here is the uncomfortable part. Your tap is not monitored in real time. Water quality is tested in intervals, which means the water you drink today is confirmed safe tomorrow. Pause for a second. Walk to your kitchen. Turn the tap on. Let it run. Listen to it. That sound feels permanent. It isn't. Just as modern wet-cured ham becomes dangerous within hours of a refrigerator failing, modern tap water becomes uncertain the moment the grid goes down. Its safety is not stored in the water itself. It is maintained by the system around it. And that system depends on power, sometimes generated hundreds of miles away. This brings us to the real comparison. The difference between these two systems is not simply about cleanliness. It is about design philosophy. One is built for efficiency. The other was built for resilience. The modern model is optimized for efficiency. It delivers standardized water to millions of people instantly, with zero labor required from the user. It allows for the existence of megacities. It is scalable. It is a triumph of logistics. But it is brittle. It is a high-dependency system. It requires a constant input of electricity, chlorine, and maintenance. It is a centralized machine where a single point of failure, a contamination event at the plant, a cyber-attack on the grid catastrophically affects everyone. The medieval model was optimized for resilience. It was slow. It was manual. It limited the size of the population. But it was low dependency. The medieval approach to survival, whether it was dry curing meat to last for years without electricity, or digging wells to access filtered aquifers, was designed to function without a support network. If the king died, the well still worked. If the roads were closed by war, the fermentation in the brewing vat still lowered the pH. Modern safety is maintained by constant intervention. And constant intervention means constant vulnerability. Every hour, the system must work. Every minute, pressure must hold. Every second, the chemistry must balance, or the illusion collapses. Medieval safety was different. It was not guarded. It was designed. They built systems, geological and chemical, that remained stable, even when no one was watching. Which system fails more gracefully? Imagine a blackout. Not for an hour, not for a day, 3 days. No pumps, no pressure, no treatment. When a modern system fails, it fails totally. You have no water. When a decentralized system fails, it fails locally. You simply walk to the next well. But we should not look back at the past with arrogance. We should look back with curiosity, because the people who built these wells and the people who cured the meats that lasted through winters understood something we have forgotten. They understood that true safety isn't something you buy. It isn't something that is delivered to you by a utility company. True safety is a relationship with the physical world. There are two kinds of safety. One is maintained by constant, high-energy intervention. The other is maintained by structural design. The tap gives you water, but the well gave them control. And control is the rarest luxury in the modern world. The question is not whether we should go back. The question is whether we still remember how systems work. When a machine goes silent, we investigate forgotten systems, not because they were perfect, but because they solve problems differently. If you want to understand the machinery of the past, subscribe.